Welcome back to the module on dynamic approaches for AutoML. In this unit, we're going to talk about population-based approaches. Now, let's first talk about this visual representation of what's going on. So here, this bar represents the performance that we can achieve with a given set of hyperparameters that are indicated by the circle and the color value that is attached, as well as this bar and the color value that is attached for the weights of a neural network. Now, in the black box view, right, what we can see is we take a set of hyperparameters and use them throughout the whole training of a particular neural network, right? So these could be different epochs at which we evaluate the neural network, and we see we improve over time and the weights of the neural network are evolving. Obviously, we can also train this in parallel. We also now want to make use of this population to not just have a gray box view on the optimization problem, but actually have a white box view. So what we now do is compare these members in the population, and we directly see that one member outperforms the others. So since we do not want to continue training the low-performing members, we do want to continue training the well-performing ones, we can exploit them. For that, we just copy over the set of hyperparameters and weights to our poor-performing member so that we have a better performing member now. And to be able to explore the hyperparameter space, well, we now perturb them. We slightly increase or decrease the value of the hyperparameters randomly and continue training the exact same weights with this new set of hyperparameters. And in this example, right, we get a much better performing neural network with a different set of hyperparameters, having switched the hyperparameters in between the optimization procedure. And that's exactly how population-based training works. We have a population, we compare the members, we discard the bad performing members and replace them with the good performing members. And then to make sure that we explore the hyperparameter space, we do perturb the hyperparameters of the well-performing models. And the authors showed that this works well, for example, here in this transformer example from 2017, where they compared random search to population-based training, and they showed that, well, the best that you can do with random search, if you sample all of these schedules as they were supposed to work well for transformers in the original transformer paper, warm starting and then decaying, the best that you can do is this. But with population-based training, right, you just sample a bunch of these different initializations and see that, well, only up here in this region, you have a really well-performing population. And over time, the decay that is discovered by the population is more strongly pronounced than the handcrafted schedules give you. So this shows that this can work very, very well already. However, population-based training does not return a hyperparameter optimization policy. There's a very important distinction. It returns a fully trained model. So the choice of which hyperparameters work well at each time step is really coupled to the neural network weights at this time step. So you do not have a general policy that allows you to train all of these different networks, but the weights that are being trained are really attached to the hyperparameters and vice versa. Now, PBT uses evolution to trade off this exploration and exploitation and is not model-based. So we could make more use of something like Bayesian optimization, as we will see, to get more improvement. But a nice property of PBT is that it is efficiently parallelizable because we just have these independent member training runs and we just really need to communicate via the disk. So we just dump our weights and hyperparameter values to disk. And if we want to replace bad performing members, well, we just load them from disk. And the same thing goes for the performance value as well. So it's very easy to implement. Now, we know that BO is very sample efficient. So the question is, can we make use of BO's power to guide the exploration in PBT? Luckily, the answer is yes. So we have seen multiple instantiations of that already. But we have to make sure that we take care of a few issues. First off, PBT can run asynchronously. So that means if we want to use BO, we either need to force synchronicity or make some uses of parallel BO that can deal with the asynchronicity of these multiple population members. But more importantly, the cost really depends on a bunch of different cost values that are induced by these different hyperparameters that we explore over time. So this prediction task gets very difficult. To make it more easy, right, we predict the cost of improvement rather than the exact cost. So we know how the cost has evolved over time. And we're now trying to predict the next evolution. And very important for our surrogate is that we also take the previous cost value into account so that we have a reference point. So we know if there's still lots of room for improvement. Think in the beginning, accuracy is very low, so there's a lots of potential for improvement. Or if we are at the end of the optimization procedure already, it's unlikely that we will make a huge amount of improvement anymore. So that is baked into the surrogate and the prediction becomes easier. Now, this combination of PBT and Bayesian optimization, like using the cost improvement and the surrogate basis, has been called population-based bandits. And it works very nice, right? So rather than using a huge population as in the original PBT, where for the transformer example, I believe they used 80 members in the population to get these good results, PB2 now can get away with 8 or only 4 members. A different approach to PBT that I wanted to take into account here is Bayesian generational PBT, because it allows us to incorporate neural architecture search. All the previous approaches to PBT or these PBT style approaches really only work on the classical hyperparameters and not on the architecture parameters. Bayesian generational PBT works as follows. So you sample an initial set of members, but not just initial weights and hyperparameters, but also different architectures. Now, in this first generation, you just do your general PBT style, but instead of copying over just the weights, you copy over the weights and the overall architecture, right? So you replace bad performing architectures with good performing architectures, as well as exploring the hyperparameter space. Now, at the end of this first phase, right, then you have a set of hyperparameters and architectures and weights that worked well in this generation. But you also want to explore the architecture space more, because here you start out with a bunch of different architectures, and here you have reduced it to just a handful of architectures, or potentially even just one architecture. So you want to sample a bunch of new architectures randomly, but also guided from Bayesian optimization. And to make sure that you can use the knowledge that you have already in the well-performing networks here that might be very dissimilar to the networks that you want to start in the next generation, you use distillation. So it's sort of a form of imitation learning where you just try to get your new architectures to imitate the already well-performing architectures that you have here. And once you have imitated them, you start a new generation, right, with these new neural networks and neural architectures, and you do your PBT stuff again, then you distill and do another generation, and that works much better than just using a fixed architecture and allows you to explore the architecture space, the hyperparameter space, and everything dynamically to get the best performing model in the end. Another approach is meta-population-based bandits, which uses this PB2 style approach to actually use warm starting or other meta-learning techniques to inform the surrogate model of BO. So if you have a bunch of different dynamic learning runs already lying around, or also static learning runs, right? You can warm start your Bayesian optimization model, your surrogate, by taking all the data into account here, so that you inform your Bayesian optimization already what has worked well in similar tasks over time. So your Bayesian optimization has the advantage of not having to figure everything out from scratch, but is warm started already at every time step. And this paper explored a variety of different meta-learning techniques. In particular, something like warm starting seems to work very, very well, that you have already an informed surrogate model to make your population-based training approach much more efficient. And you can also think of this as having a larger population in the meta space. You only use the knowledge of those members that are most closely related to the task that you're really solving at this moment. So to summarize, dynamic tuning is done via evolution in this unit, right? Population-based training and its variants, explore hyperparameter schedules in this evolutionary manner. And the successors incorporate prior knowledge in various ways. PB2 builds a surrogate based on these previous performance values. The generational approach uses distillation to transfer knowledge across different generations in the task, and Meta PB2 uses a variety of meta learning techniques for BO to incorporate prior knowledge of completely different runs. And the most important thing is PBT style HPO does not produce a reusable schedule. It gives you a well-performing model in the end, and you can identify trends that have happened over the optimization procedure, but you cannot one-to-one, use the schedule for retraining. Thank you very much.